So let's start by understanding the question together. A game of skill. You and your friend are playing a game on a board with n+1 positions numbered from 0 to n. So let this be our board. The positions are numbered from 0 to n. Each of you has a meeple initially placed at position 0, and the goal is to move it to position n. Each of you has a 6-sided die, and you take turns to roll your die and move your meeple as many positions forward as the number shown on die. If a player is at some position x and rolls an I such that x plus I is bigger than or equal to n, okay, their meeple lands on position n and they win. So this is the winning condition. So if we're at position x and we have a die roll of I, if x plus I is bigger than or equal to n, it's a win. Nice. We have decided to cheat and have loaded your own die, so the probability of you rolling I is pi for every I. So this is my dice. It's pi for I starting from 1 going to 6 for each output. Your friend is using a fair die, so for them the probability of rolling I is 1 divided by 6 for every I. Okay, it's a regular die here. Your task is to answer the following questions. What is the probability that after you and your friend have played one turn each, your meeples are on the same position and that position is indexed with an even number? Okay, this is easy. Conditioned on your meeple landing on position 7 after your second die roll, what is the probability that your meeple landed on position 3 after your first die roll? This is also easy. Independently of your friend's meeple's behavior, what is the expected number of dice rolls it will take you to reach position? So this is actually quite complicated, like relatively more complicated. It will probably require some DP. Okay. Input. The first line of the input file contains a number t of test cases. Each of the t-test cases is described as follows. It starts with a line that contains 2 integers and q, separated by a space, denoting the index of the last position on the board, and the type of question you're supposed to answer. Okay. The following line contains 6 real numbers separated by spaces, denoting the probability of rolling an I with your loaded die. It is guaranteed that the sum of all those pi is equal to I and 1. Okay, nice. So there are n, q as integers. Last position of board, and this would be the question type. Then in the following we have 6 real numbers, and this is the probability of our dice. So output. For each test case, output a single line with the answer to one of the questions stated above. The Q value of each test set determines which question you should output the answer to. For example, if Q is equal to 3, you should output a single line with the expected number of die rolls. It will take you to reach position N starting from position 0. Your solution is going to be accepted if it has an absolute value or absolute or relative error of at most 10 to the power of minus 5. Okay. There are 3 groups of test sets worth 100 points in total. For the first group of test sets worth 30 points is probably for question 1, 30 points for question 2, and 40 points for question 3. Okay, a sample case for n is equal to 2 and question 3 is given, but I don't think we need it. I just left these notes for you to observe if you want. Okay, let's start by reading the input. So as usual, we have our main function. It already reads the t, and then for every t, it calls the test case. Then there's a test case function, and we're going to put our solution here. Okay. Input using in.java class. It already reads n. We're going to read Q2. So n was last position of the board. Q was the question type. Nice. And then there will be 6 real numbers to store for us, because this is our malicious dice. So let's do a double p array. It's important to do this one double, otherwise the solutions won't be suitable for you, and even though you make everything right, you will get 0 points, which will frustrate you a lot, which will be really sad. So there will be y7. So I want to encode this as it is in the questions. That's why I'm going to start from index 1 till index 6, and I'll just leave index 0 empty. So, but this is just a matter of style. If you want to do it differently, just do it differently. This is just what's easy for me right now. I don't want to think about it every time I want to use a probability. Oh, is it +1? Is it -1? I'll just use it as it is in the question. So pi is in we double. Oops. Yes. I just started from 1 and went till 6. So yeah, it's just a matter of preference. So next thing would be the output. So the output would be, again, double typed. Why is this important? I mean, it's obvious why, but like you have to really pay attention to these things. If you're sure of your answer, but like you're still not getting the points, check if your typing is correct. Everything about probabilities has to be double. Otherwise, it's gonna be casting it into integer, and it's gonna be losing you a lot of points. So I'm going to define answer and then output it differently for each question type. And then for each question type, I'll have an if condition like this that would change the answer value according to the question. So yes. Now let's start with question 1. So let's start by answering question 1. What is the probability that after you and your friend have played one turn each, your meeples are on the same position, 1, and that position is indexed with an even number? This is the second condition. So how can this happen? Both of you could be in position 0, both of you could be in position 2, both of you could be in position 4, and both of you could be in position 6. Okay, the probability would be the sum of all of those conditions. But both of you can't be in position 0 because you have to roll something and then move out of the position, because it's given that you have played one turn each. So this is equal to 0. Then for each case, the probability of both of you being in position 2 would be equal to the probability of you being in position 2 multiplied by probability of your friend being in position 2. Why? Because two of those events are actually independent from each other. That's why you can just use the definition of independency, and then it would be equal to P2 times 1 divided by 6, because your friend's die is fair, but your die is not. And then the same holds for position 4, P4 times 1 divided by 6, and then for position 6, P6 times 1 by 6. The only thing now that is left for us is to code this. So let's code question 1. As we said, for the answer of question 1, we're going to calculate all these 3 probabilities, but it's relatively easy because they're independent, and it's just P2 times 1 by 6, P4 times 1 by 6, P6 times 1 by 6, and then we're going to add them. But what's important here is to keep everything double. So this is not the ePro class. Instead of thinking about, oh, what's the casting? Oh, is it this? Is it that? Don't worry, just keep everything double and you're gonna be safe. All right? So that's what I'm gonna do. And it also saves times. Saves time, and it's also good to not complicate this. So just complicate things where it's necessary. If it's not, just choose the simplest solution and be safe. That's the way. So this is just the answer for question 1. Let's see if it's compiling. Wait. Oh no. Okay, let's see. Nice. Let's see if the testing is correct. Right, we got the correct answer from question 1. Nice. Question 2. Conditioned on your meeple landing on position 7 after your second die roll, what is the probability that your meeple landed on position 3 after your first die roll? Okay, so this asks for the probability that, given that your meeple landed on position 7 after second die roll, what is the probability that your meeple landed on position 3 after your first die roll? So this is, for this task, we're trying to calculate this condition probability. And from the definition of Bedingtawahrscheinlichkeit, this over here is equal to probability of position 3 after first roll intersection with position 7 after second roll divided by the probability of position 7 after second roll. Okay, this is just the definition of Bedingtawahrscheinlichkeit. And if you guys consider each of the probabilities separately, position 3 after first roll intersection with position 7 after second roll would be probability of rolling 3 times probability of rolling 4 in the second one. Why? 3 plus 4 is equal to 7, and those 2 rolls are independent from each other. Nice. And then position 7, then the probability of position 7 after second roll. How can this happen? There are 6 cases that this could happen. You roll 1, and then you roll 6, you roll 2, then you roll 5, you roll 3, then you roll 4, then you roll 5. You first roll 4, then roll 3, you first roll 5, then roll 2, you first roll 6, then roll 1. See that those 3 are the same with those 3. Why? Because they're independent. You can basically change the order. And for this probability, we basically calculate P1 times P6 plus P2 times P5 plus P3 times P4 all the way till here, times 2 because those 3 are the same. So that is the probability for that. And then if we divide those 2, we will have our answer. And that's it. Only thing that's left for us is to code this. Now let's move on with question 2. For this, we're gonna calculate 2 probabilities, this one and that one. So let's call the first one double probability of, let's say, A and B. I don't know. And the next one double probability of B, because that's how it is in the formula. So A and B would be P3 times P4, P3 times P4. Here you can see why I picked those indexes. I don't have to think about anything. And the next one would be P1 times P6 plus P2 times P5 plus P3 times P4 times 2. Okay, let's go. Times, again, I'm using double for everything. Yes. And we have it. Now, only thing that's left is to divide those two. So now we assign our answer with the division of those two. Everything is double, there's no need to worry. But always check the doubles. Always check if everything is double. So let's see. Great, we have the second correct answer. Our green bar is looking good. Question 3, the hard one. Independently of your friend's meeple's behavior, what is the expected number of die rows it will take you to reach position? Okay, so for this we first define the random variable expos by saying that it's the number of die rows to reach and from position. Okay. And a simple DP task would be from last semester, for example. If we knew the dice output for every step, then it would be like expos is equal to 1 plus expos plus last output, right? If we knew the last output, this would be similar to the jumping game. So like frog jumping, you jump, you knew the die roll, you jump, you knew the die roll, you jump. But the problem here is our last output or last die roll is just not defined a priori. That's why we're trying to find the expected number of it. So it's just a bit harder. And the probability comes into play. So, okay, first things first, remember the definition of expected number. For the definition of expected number, you're going to sum up the probability of an outcome will happen times the outcome for each of the outcome. That's literally like the weighted average, as we called it in class. So this is the definition of expected number. And then the expected number of expos would be then, what can the outcomes be? We're rolling a die, right? So the expected outcomes could be at each spot, so at each position, we roll a 1, we roll a 2, we roll a 3, 4, 5, or 6. So, and then, probability of rolling a 1 would happen, probability of rolling a 2 would happen, probability of rolling a 3 would happen, would be probability that it will happen, and then the outcome would be the following. So the die roll that we just did plus expected number of die rolls to reach n from position post plus I, because that's exactly expos plus last output. Last output is I, right? So this is exactly that. Okay. So as you can see, if we knew the expected number of expos plus I, we could basically calculate the expected number of expos. From this, you guys need to understand that this is in fact a DP task. Why? Our solutions depends on the solutions from before, or in this case from afterwards, but if you start the indexing from n and then you come till 0, it's like the solution from before. So we're going to calculate from n going till 0. So our solution will depend on solution from before. So the solutions from before, Eureka, we're going to use dp. Okay? And then if we define dp pos as the expected number of x pos, then our problem will exactly look like this. So this is our dp calculation. Okay? And then where will be the answer? At x0, right? Because x0 would be exactly the number of die rows to reach n from position 0. So that is what we're going to do. And let's really carefully code this. So let's first start by defining our dp table. Wait, let me just put this a bit above. So, okay, double is equal to, wait, let me keep it low, new double. Okay, what is the size? There are m positions, but I want to do it +1 for initialization. So there's that. And then I'm going to initialize the first position with 0, 0. Okay. We're going to start from the last position, so position n-1, and then we're going to move on till position 0. So we're going to calculate decreasingly. So let's define our for loop. I'm just going to call the index like position to be more clear. Oops. Okay. So what are we going to do for each loop? For each loop, we're going to have to calculate this sum, right? So, okay. So let's define a variable named sum. And then let's have another for loop for this, because we have to. Okay. Nice. So then let's say, okay, the next position is position plus I, right? Because we are varying our I. And there are two cases that can happen. We can either win, so our next position is bigger than or equal to n, or we're somewhere in between. So if next position is bigger than or equal to n, we're going to do something else. We're going to do something. Okay. And at the end, we need to assign our dp position with the sum value we just calculated, right? So only thing that's left for us is here. And let's start with the else condition because we have it here already. So it's gonna be probability I. So let's add it to the sum. It's gonna be probability I times 1 plus dp of next position, because next position is like position plus I, so we already had this one. So what if the next position is bigger than or equal to n? This would be out of bounds then. We don't want that, right? So instead we're going to say it's 1 plus dpn, because that's how we initialize it. We don't need to do anything else. We're just gonna jump. Okay. And lastly, let's assign our answer to be dp0y, because dp0 holds the number of dice rolls to reach and from position. Expected number of dice rolls to reach and from position 0. Okay. Everything is looking okay to me. Let's check. Compilation successful. Great. Best feeling ever. I hope you guys have the same full green bar for both of the tasks. I'm wishing you the very best for each of your exams, and hope to see you around. Good luck with everything.